on stage Illia from Near Protocol. He has just finished, the Near Protocol guys have just finished their Hack the Rainbow hackathon. That was a huge success. But Illia is going to chat to us about sharding for scalability and development experience. Illia, can you hear us?
Yeah, thanks, Simona, for introduction. Well, it's great to be here, and welcome everyone. I hope your hacking has been starting well. Yeah, let me kind of talk through some of the sharding, and I'm sure with all the news around these two, there's a lot of questions. So I'll try to kind of cover some of the topics and surface some of the interesting questions. But if you have any other questions that I didn't cover, please ping them in the chat, and we'll respond at the end. So first I wanted to just mention Near itself. So Near is a proof of stake layer 1 that's specifically built with experience in mind. So which covers user experience and developer experience. And scaling, if you think of it, is part of this kind of experience, because as your users, as your user base grows, as your application gets more usage, you should not be dealing with, scaling your application. And also your users should not be dealing with, high fees and figuring out, what to do with all of that, right? Like this stuff should be completely transparent and just work. And so kind of the general idea, right, is to build the experience that matches kind of the Web 2, right, the existing internet, and in such a way that, you can bring in non-crypto people and they can just use applications. And it's been pretty important to obviously interoperate with Ethereum, because this is where kind of most of the existing developers and users are, but we also want to onboard lots of developers who are coming new. So let's talk about scalability. So let's start with how you cannot scale, right? And so there's been a lot of kind of new consensus algorithms where people would be, providing an idea how to scale the blockchains with, some amazing consensus algorithm, and being able to do stuff that is faster. There's been a lot of also changing from blocks to trees, to DAGs, to some other data structures which are presumably allowed to do something faster, or switching to different proof of, right? And to be clear, obviously proof of work, it has inherent limitation, and that limitation actually is in the fact that you first need to organize a block, and then you need to mine it. And that mining time is actually adds on top of your kind of execution time. And even then, actually, that is possible to pipeline. So in theory, it's possible to optimize that and actually have throughput faster with proof of work, but it's still not the bottleneck. The actual bottleneck is not data structures, it's not consensus, it's not a proof of, it's actually just executing. And the reality is we want to run a smart contract platform, right? We want to run generic code, and this code needs time to execute. And so this is actually just syncing the Ethereum blockchain with fully downloaded, right, snapshot of all the blocks. And so there's no network, there's no consensus, there's no data structures, it's just purely EVM execution. And as you see, there's a limit how much gas you can push through in a second. And so EVM itself, on a kind of somewhat default hardware, right, maxes out at 200, 300 transactions per second of normal smart contracts. This is real smart contracts on mainnet. And this is the bottleneck, right? It doesn't matter if you switch to, proof of something, right? Proof of authority, it will be the same way. It doesn't matter if you have the magical pipelining and stuff like this. So the only other option, the way to scale, right, is either significantly optimize transaction processing. So this way includes, changing from EVM to another kind of execution environment, right? So WebAssembly is faster, but it has its own challenges. There's kind of Berkeley network, the Berkeley system that Solana, for example, uses, which is faster. You can put execution on, for example, GPUs and stuff like this. The problem is all of that really works if you have a homogeneous load, because if you only need to do payments, for example, you can scale, pretty dramatically, because, you can parallelize that. You can have lots of processing power, on one machine going really quickly and doing things in parallel. But at the end, actually one of the core limitations is not an interpreter, it's actually hard drives, right? Just being able to randomly access hard drives is hard. So, and again, like you can put more hard drives, but like there's a limit. And so the other option is just split the work, right? I mean, that's an option that the whole internet is using, right? Google is not running on one machine. Facebook is not running on one machine, right? There's lots of machines running in parallel, processing things in parallel. And so this is what's called sharding, right? I mean, this is not a new concept, right? It's been around for probably 2 decades, if not more. And the idea, like, we need to scale up. Like, we cannot have network, pretty much everybody in the network doing exactly the same work. They need to parallelize. The problem is, this is very hard. And this is hard because there's a lot of kind of technical challenges on how to make sure that everybody's doing the right thing, how to make sure that the chain is correct when you don't actually run all of those things. So I'll just cover a kind of like a little bit of a difference, but between the kind of default sharding approach and also what we've been working on. But so the general idea, right, is you parallelize the work, which means you kind of need to do a bunch of stuff in parallel, which the kind of naive approach, or like the approach everybody starts to take, including us, is to parallelize the chains itself, run multiple chains in parallel, and then in some way to kind of link them together and do this, like use this as a way to communicate between them. And so this is an approach that, originally like ETH2 took, it's approach originally we took, it's approach that Polkadot implemented, it's approach that kind of, if you think of Cosmos as a sharded chain, which it's not, and it's a little bit different, but like in general, the concept is the same. It is by scaling by a lot of chains. But like one of the core issues with this, and we'll cover like a lot of other interesting issues, is just like it's inherently complex and has a lot of kind of repercussions. And so the approach we're taking is really parallelizing the blocks. And I also draw some parallels with other approaches as well. So what are the kind of technical challenges with sharding? Well, one of the big challenges is if you think of any proof of stake system, usually if you have a 1/3 malicious and network split, you can actually take over the network, right? So either stall it if you have 1/3 plus 1 or of stake, or if you have a like network control, you can actually do some like fork of the network. And 1/3 of stake, usually like you can incentivize growing the stake. It's still, sadly, in current proof of stake systems, we still have a pretty big concentration, but hopefully over time this will grow. And you also need to kind of track, like you're pretty much saying that because we assume that there is less than 1/3 of malicious actors been on the network, then pretty much the whole, like by induction, right, the whole chain is valid because like every other block is every next set of validators is selected by the validators that were correct. And you need to actually like have some intersection between when the validators are rotating, because they need to actually download the state. So that's how this works. The problem is that if you think when we're doing sharding, right, what happens is that in each shard you have you need an assumption of 1/3 malicious, and so this leads to a problem that if you sample kind of for a long term, right, you just sampled it and just run with that, this validators can get corrupted, right? And sampling, like let's say you have 10 shards, 100 shards, sampling into that will pretty much lead to like the probability, if less than 1/3, like if 1/3 or like even 20% is malicious, like sampling into one of the shards can be higher. But also what's more important is that people can get adaptively corrupted, right, over time. So you need to actually rotate validators across the stack and make sure that they are pretty much cannot know which shards they're validating too much in advance. So that's where like this thing come in, is like you pretty much rotating validators, but you need to give them some heads up to download the state of the next shard, because compared to a normal like single chain, right, where all the nodes have the full state of the whole network, now you only have a partial state. And if you are responsible for validating next shard, you need to go and download the state of that shard before you are able to validate. Otherwise, you'll be lagging. And I'll mention data availability in a second. So the other problem is what happens if somebody actually did attack, right? Let's say there is a more than 1/3, like 2/3 of malicious validators in one of the shards, because like in general, the numbers are smaller of stake. And the problem is that the other shard cannot detect this very easily, right? It's not validating that shard. It's not actually validating state transition. It only kind of keeps track of that shard. So, and like the kind of the attack would be to send, let's say, invalid state, like for example, say, well, all the money are mine on this shard, and then send them to another shard to exchange and exit, right? And so maybe like network, like everybody will detect this, but it will be too late and people already stole the money. So the kind of the general approach to this is called fisherman, and this is where somebody can pretty much tell the other shard that, hey, something is wrong in this shard, and they provide a fraud proof, right? And so this is similar to like what we've just heard in kind of Plasma's approach as well, where if something is wrong on a Plasma, right, then somebody can provide a fraud proof to the Ethereum and exit pretty much from this. And so the problem here is, and similar to Plasma, is data availability, right? So you need to, somebody needs to actually have a fraud proof generated in the first place to be able to prove that something went wrong, right? And so if this malicious actors did not produce a block, right? If they did not post a block to the network, right? Then this, let's say, honest actor in that shard has no way to really create a fraud proof and prove it to the other chain. The other side is obviously finality, right? So like if you send a cross-shard transaction and there's a fisherman, right? The fisherman needs some time, right? So in case of Plasma, it's 7 days. Big part of it obviously is because of gas issues and, you know, transaction censoring and a bunch of other stuff. But this challenge period needs to exist. I mean, it can be shorter, but like this is the finality of this cross-shard transaction, right? We cannot execute it until we make sure that there's no fraud proof coming in. And there's no like, there's no way to not prove there's not going to be a fraud proof, right? So there's no way to like speed it up. And so this creates a lot of issues on like just kind of creating a fast cross-shard transactions between chains. The other thing is like, if you, for example, do speed up, then you need to actually like roll back a bunch of stuff, right? You need to fork off, like if you allow a transaction to go in and you just kind of revert it, you need to revert like kind of a cascading effect of all the shards that get affected. And this also can be very complicated. And then the data availability part is what I mentioned, right? If validators did not post invalid block, right? There's no way to prove that there is an invalid state transition, and like next validators cannot do anything about it. So important is obviously to have a mechanism to provide data availability to the network. And so one of the main solutions that pretty much everybody uses, so it's us, Polkadot, and other folks, is to pretty much use erasure codes. And so this is the idea that when somebody produces a block, or in our case, a part of the block, they need to send out parts, right? So they need to send out erasure coded parts of this block to other participants. And only if those other participants saw these parts, they will include this block as a valid. Like they don't need to validate it. They don't need to make sure the state transition is correct. They just need to know that there's data availability. So what you do, you weave into consensus, right? You actually include this into consensus that you can only accept those things that you saw parts of. And if you have enough of these parts, so enough people are tested to having these parts, then it means that actually from these people, you will be able to reconstruct this this block that was transmitted, right? So even the original block producers, or in our case, chunk producers, disappear. You'll be able to reconstruct just from these parts the full information. And so just for context, erasure coded means that it's a special encoding that even if you only have, like in this case, you have 6 parts, right? To split the data into 6 parts, and any 2 parts is enough to reconstruct the original data, right? So it's kind of a 3x duplication of information that's like any of the 2 parts is sufficient. And so this mechanism is kind of at the core of like our approach, and Polkadot as well uses this to pretty much make sure the data is available across the network. And so I mentioned before, right? So we transitioned from this idea of having multiple chains running in parallel to having actually one chain and sharding blocks, right? So this actually allowed us to do a lot of things, including, because we have now one blockchain, this allows to really simplify the whole challenging things, right? Because if there is a issue that have happened at some block, right, we can just roll back the whole chain with it, like that contains all the malicious state transition, right? So we don't need to like find, you know, a bunch of chains and figure out where they went wrong and roll them back. You just have this kind of one finality for all of them. And so this provides kind of a better experience, and it's also just easier to implement. Like that being one of the core things, because obviously like this stuff is very complicated and it's very hard to test. So the other thing is obviously it provides a better cross-check transaction functionality. And so we can move into this. I think like a few things important to mention here, which like if you think of it, what rollups are and what plasmas are in a way is kind of a specific versions of this as well, right? It's all a way to run some kind of computation outside and then settle into the main chain, where main chain is providing data availability and is providing the kind of finality security, right? The challenging system, right? So in this case, like in our case, we're using kind of our like full chain to do this, but you can imagine this like full chain would be Ethereum, and then all the shards are just running as a parallel chains. And that's kind of what like plasmas and optimistic rollups are. And then like they have all the same problems that I mentioned, right? They have a 7-day challenging periods to do this. If it's optimistic rollups, for ZK rollups, right? They can actually prove the full state transition, so they don't have this problem. And this is kind of how it all links, right? In reality, all of these methods really just like different ways of handling these problems that I mentioned. Now, the important piece is how to communicate between, right? So if you have a multi-chain environment or multi-shard environment or multi-rollup environment, right? It actually becomes really complicated how to connect them together, right? And specifically, there's a lot of kind of issues around rollbacks, right? So if the other chain rolled back, what do you do, right? Like, you know, if Ethereum rolled back, if you are optimistic rollup, you actually need to roll back as well, right? Because you're tracking Ethereum. If you're a separate chain and there's a rollback, like what do you do, right? There's gas costs issues, right? It's because like if you're trying to send a message from one chain to another chain, if the gas is different there, it's in a different token, right? Like who's going to pay for it? How are you going to calculate when you're sending transactions that you prepaid the right amounts and stuff like this, right? You now need to attach like another token or something else. The critical state recovery is around rollups, is around rollbacks, right? If something happened, right? If a rollup producer stopped, right? What do you do? Like it's a mass exit. It's a kind of, you know, like you roll back some stuff, you prove things, you make sure that you have all the data availability. But like what happens with all the transactions that are in flight, right? What happens with all the cross shard? Like you were calling from here to here, like what happened with them? And it's important to figure out like, what's the order of execution that will happen on the other side if that happens, right? If like optimistic rollup producer stopped, everybody's mass exiting, but you actually had a proper exits as well, and they'll not get executed at the proper time because they all like waiting for 7 days. It's like, what's going to be happening in all of these cases? And then the important part is composability, right? If you have like 2 rollups or 2 shards or 2 chains, right? If the communication between them is complicated, it has gas, it has all this like 7-day waiting periods, or even like a minute waiting periods, like composing contracts, composing applications becomes super complicated. And especially if you want to also receive a callback, right? And hear back about what happened on the other shard. So with Near approach, right? We have pretty much been focusing on fixing all those issues and making the experience really smooth on how this works. And think of it, right, because we have one blockchain, like from a developer perspective, you actually don't need to think about kind of shards and sharding in general. Like if you go to our Explorer right now, you actually will not see, we're running one shard, we have another test network with 4 shards, but there you will not see any difference because the sharding is completely hidden from the developer. And the kind of main thing that we propagating is that all the contracts working asynchronously. So the communication between them will not happen within one atomic transaction. It will happen within the next block, right? So you're pretty much creating a message and you're sending it to another contract, and another contract will execute it in the next block. And this is similar to like message passing in Erlang or any other like similar language. And first of all, it removes any kind of reentrancy problems. Second, if there's any rollbacks, this can be handled cleanly because all those receipts are kind of staying in the block, and then like you roll back, you restart it, and you have all those receipts just coming in, and you need to process them. They are mandatory to process before any other transactions coming in. That are like all the receipts, like these messages passed from one contract to another, kind of coming in the beginning of the next block. It solves the gas costs because we kind of pretty much like one of the core ideas is dynamically balancing contracts between shards. And so this would allow to kind of even out the gas costs over time. So it will not be like immediate, like, within a like few hours, you may have spikes, but like over long term, right? If there's some contracts that are more used than others, it will pretty much even them out and split them between different shards evenly, maintaining kind of the balance. But importantly, it kind of has this composability property, right? Because now you can realize that the contract will be delivered, right? And you'll get a callback. And so, and like the only thing that you need to handle is the fact that it's not atomic, right? So you do need to handle kind of state reversals somewhat manually. There's like few tools to do that on developer side, but you do need to kind of handle like a failure of the execution of the contract. The benefit is now you can handle the failure of execution of those contracts, which you actually couldn't on Ethereum. So you can actually call contracts, see if it fails or not, and execute some logic based on that. So think of it try catch. And yeah, so this callbacks is kind of allows you to like attach obviously near as a resource. It allows you to attach information and receive it. So here's an example how this works. So you pretty much, this is in Rust for WebAssembly contracts. You can create, you can call is whitelisted based on some interface. You provide it the kind of contract that you want to call, some arguments, no deposit in this case, and somewhat of gas. And then you have a way to attach a callback to this execution on one of the methods on the contract itself. So it pretty much will call it, it will execute something, and then return. And actually that contract can call something else, and then process something, get callback, get callback, right? So you can actually have like a pretty long chain of calls that processing. Now, so this is actually like, this is very useful. You can actually have like a very interesting like multi-shard contracts now built on across this. You can also shard your existing contracts. So for the users, like for example, for a token, we actually have some proposals for sharded tokens because tokens actually don't need to have all the accounts in one shard, right? You can actually shard them as well. And there's like a few other applications that kind of need the scale of multiple shards. So going beyond even one shard, but there's also a lot of the DeFi specifically, right, has some issues with async calls, and like this will be very clear because one of the kind of benefits of DeFi, and like I usually call DeFi is just a programmable exchange, right? So if you think of it, you deposit money into exchange, right? And it gives you a bunch of tools. I'm talking about like NASDAQ or, one of those exchanges. They have a bunch of tools already pre-built on that exchange. You can trade, you can do stuff. And within that exchange, right, everything is atomic, everything very fast. Nobody can front run you, hopefully. And then you can go to another exchange, right? So what Ethereum with DeFi provides in a way is the ability to deploy new contracts, new code into this one kind of one exchange, one place. And so this is provided by like ability to execute kind of atomic transactions, across multiple calls. So it does become complicated to do that for async calls. And one of the main issues is that because if you think of it, like if you have two contracts that have async and you have some kind of logic flying between them, people can try to front run you to go after this contract earlier on, right? And so there's ways to mitigate that in this kind of multi-async environment, but obviously this like, as the system grows, right, as you have more and more pieces working together, this becomes more and more complicated. So there is a value in sync calls. And so we are actually just launching the EVM, what we call the vaults. So in a way, it's like a one shard of a EVM. And I mean, it can obviously scale with, but goes up to one shard. And within that EVM, we have synchronous calls, right? So within that EVM, it behaves like Ethereum. So you can think of it as just launching Ethereum shards inside Near. Actually, originally, it was done as just a smart contract. So we literally compiled EVM code and just launched it as a smart contract on Near and had like original initial testing. But now we pre-compiled it and kind of speed it up. So that gives us like, whatever the raw performance you can get from the EVM, you get that. The interesting thing is you can have many of them. So you can have multiple EVMs in parallel running and have async calls between them. So you can think of it like can have multiple exchanges or some other contracts maybe that are not exchanges that dealing with like, in-game items or whatever that don't care about like specific DeFi stuff. And so you can still async communicate with them within one block. So you have like all the same functionality and you can communicate with those other contracts. And in a way, this actually works as like, you can call it realistic rollups, right? Because what optimistic rollups is you execute something off chain and then you post it on chain as a data and then you don't execute it, but then you wait for anybody like pretty much optimistically it's there, but then somebody wants to challenge, you need to wait for a period. Here you actually execute the state transition of EVM right away and it's like valid right away, right? So like I call it realistic rollups. I mean, even better was if there's EVM that's running like off chain and they just post all the data and it gets valid on chain. But because we have 1 second blocks, you don't even need to do that. It pretty much gets the same performance. So like each EVM vault will be like as fast as like Optimism or any other kind of EVM engine running as a separate thing, but it will work within this whole environment. And there's like kind of going forward, there's some ideas how to scale even this up, but this is kind of future work. So before kind of ending, I have one last thing I want to mention. So Simona mentioned about our Rainbow Hackathon. And so this idea is like in a way, like from perspective of Ethereum, Near is, is kind of this multi-sharded environment in which you can run contracts, and with EVMs, it's like many EVMs, and there's no kind of like with this bridge, we're actually connecting those two environments. And from Ethereum side, EVM is from Ethereum side, Near is a side chain, right? With many side chains connected together with EVM and with WebAssembly. From Near side, Ethereum is just another shard, right? Because you can actually call into it and get responses as callbacks and kind of have all the same functionality, just with a little bit of lag on the finality and also timing. And so this is pretty much facilitated by like a light client smart contracts on both sides that are providing you pretty much this trustless, decentralized way of connecting to chains. And it's done in a very generic way where you have like multiple like levels of smart contracts that pretty much provide connectivity. And as a developer, you can link in any way and prove any fact about the other chain. Just to finish up, one of the main things we've been doing is really focusing on education in the space. So we actually have two series, one on YouTube and one as a podcast. One on YouTube is called Whiteboard Series, and it's about kind of talking about protocols and talking about kind of how they work on the whiteboard in depth. It has, Ethereum 2, Cosmos, Polkadot, Optimism, Matic, and I think there's like over 40 protocols now. And then the Open Web Collective is building the Open Web podcast is a podcast about entrepreneurs and builders and investors actually coming together and sharing information, sharing kind of insights on how to build businesses and how to build in this open web. So keep building. Join us at near.chat. I mean, if you are interested in kind of expanding your business, we have a protocol agnostic open web collective, which is really a incubator and accelerator for companies in open web. And if you just want to learn more about Near, there's open chat, and I'm open for questions.
Awesome. Thank you so much, Illia. I think my favorite piece was realistic rollups versus optimistic. That